All right, so somebody asked about exercise 1D, question 5. So that's on page 31 if you're following along. And basically, it's a picture starting with a square, connecting the midpoints to make another square, connecting the midpoints to make another square. And you can do this forever so that there's always littler squares going inside and inside. And there's two different things that we're going to look at. One is a spiral, and then the other one is sort of, well, first one's a spiral made out of the lengths, and the other one's a spiral kind of connecting the different areas. And the first part tells us that the length of the largest square has a length of 2 units, side length of 2 units. So let's just go ahead and write that as the first side length is 2 units. And then I want to figure out what the second side length is for this square right here. And what I notice is that's a hypotenuse, and it has a right triangle. Each of the legs is half of the big square. And so what I notice is that S2 is the square root of 1 squared plus 1 squared. Or if I want to simplify that, they're going to be the same. So it's 2 times 1 squared. In other words, it's the square root of 2. Similarly, if I want to look at S3, S3 is the hypotenuse. So it's going to be the square root of 2 times half of what S2 was. 2 times half of what S2 was squared. Because S2 has a square root of 2 side length. And so half of that makes the legs of the triangle, and you just do a squared plus b squared. But they're the same, that's why I have a factor of 2 on the inside. So this becomes square root of 2 times a fourth times 2, which all cancels out to be the square root of 1, which is 1. In general, what you'll see is that Sn is equal to the square root of 2 times 1 half Sn minus 1 squared. And we can simplify that to be the square root of 2 times 1 half Sn minus 1. So what I'm noticing is that we have here a geometric sequence with an r value of square root of 2 over 2. And it'll be important later that this value is less than 1, because you can continue this forever. So that's why I'm thinking of infinity and convergent sequences. Okay, so we just kind of analyzed it in general. So what about the length? So I guess part A says to find the length of the second, third, and fourth squares. So we already have S1 is 2, S2 is square root of 2, S3 is 1, S4 is square root of 2 over 2, because I just multiplied by r. All right. Now, use your answer to part A to find the length of the spiral shown. It looks like the spiral in the picture is the first, second, third, fourth, and fifth squares. But the spiral, let me draw it out in green. The spiral doesn't just go one side length, it goes 1.5 side lengths. So it goes 1.5 side lengths, 1.5 side lengths, 1.5 side lengths. And so each of those can be factored out in front. And so I'm just going to say it's 1.5, or I can write it this way. The sum from n equals 1. And it looks like it's the first, what did I say, 5 squares? 1, 2, 3, 4, 5 squares. So like this is a way that you can represent it. In other words, it's 1.5 times 2. Well, I was going to write out all 5 of the terms, but I can actually just use my geometric series formula. There's a finite number of geometric terms, and so I can just write it like this. The first term times 1 minus r to the n, there's 5 of them, over 1 minus r. like that. I'm going to pause for a second and grab a calculator because I don't want to do that by hand. All right, got my friend the calculator. We can do 1.5 and then 2, 1 minus root 2 over 2. Oops, need to put that in parentheses. To the fifth divided by 1 minus root 2 over 2. Of course, I could have simplified that before trying to just plug it into the calculator, but I decided not to. So we have 8.432. Okay, round it off. So there we go. Okay, part C says what happens if you do this for indefinitely. And so instead of it being the finite sum formula right here, uh, basically when you do an infinite sum, this part of the formula that I'm crossing out in green disappears. And so what we'll get is 1.5 times 2 over 1 minus root 2 over 2. And so that becomes, should definitely be a bigger number. I don't know what exactly it'll be. Let's see. I got 10.243. Make sure you're checking my numbers here. There's always the chance that I make a mistake on the calculator or anything like that. All right, the second part is, or I guess question parts D and E are talking about shading in the triangles. So instead of looking at it as a sequence of lengths, we're looking at a sequence of areas. And so the picture looks like this. You have this, 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 etc. And so it's just taking one of the corners of each of the iterations there. And so in the book, we have 1, 2, 3, 4, 5, 6, 7, 8 of the shaded triangles. And each of those triangles has an area of, so the ith area is just going to be length times width over 2. So we're going to have 1/2, and each of the side lengths is SI over 2. And so then those are going to get multiplied together. And so I guess if we simplify that out, we can say that the area of figure I is SI squared over 8, because there were 1/2, and then I squared the denominator of 2. And so for part D, what we're going to do is we're just going to add up the first 8 of them. And so that's going to be the first one uses so I should think about what the R value is to get from one area to the next. And so the R value is going to be squared because we're talking about area here. And so for my AI here, to get from one SI to the next, I multiplied by square root of 2 over 2 squared. And so my R value for this problem becomes 1/2. And if you look at it visually, that kind of makes sense that the triangle shown is half of the shaded area. And so we have the first term has an area of 1 because the S1 was 2. So square that. Oops, not 1. 2 squared is 4. So the first triangle has an area of 1/2. I'm using the geometric formula. 1 minus 1/2 to the 8th over 1 minus 1/2. Sorry, just trying to squeeze it in here. And that's going to come out to be, let's see, the 1/2s will cancel, so it's just 1 minus 1/2 to the 8th. That gives me 0.996. And then part E, just like before, is the same answer. Let's move my little face out of the way. Without the r to the n, because that tends to 0 as we add infinitely many of them. And so we just have 1/2 over 1 minus 1/2, which comes out to be 1. So if there was an infinite number of those triangles, it would shade in 1, the area of 1. So that's problem 5. Please comment or ask questions if there's anything either I did wrong or that you want more explanation on. Thanks.